Welcome back. So, in today's video lecture, we will look at what is known as the Young-Laplace equation. So, in last class, we looked at the derivation of Young-Dupré, using which we obtained a relationship between contact angle and the surface energies, right? So this equation, Young-Dupré, was very useful. We saw that it is, Young-Dupré will be very useful when you want to, assess the nature of the surface, whether it is hydrophilic or hydrophobic, using the parameter called, contact angle, three-phase contact angle. But in today's video lecture, we will look at Young-Laplace equation, right? And we will look at how it can be, how the governing equation can be obtained, right? So in general, Young-Laplace equation is used to understand or predict the equilibrium shape of curvature, right? We know that whenever we consider curvature, there will be the pressure difference across the interface, right? And there is also additional force that comes into picture. That is nothing but surface tension force. As a result of pressure as well as surface tension force at equilibrium, depending on the forces that are acting, one would get definite equilibrium shape, right? And so we will look at in today's video lecture how we can use this use this force balance equation and to arrive at a generalized or general Laplace pressure equation. Okay, right? Let's begin. Right? Yeah. So as I explained just now, so the pressure difference across the surface, okay, is what we are going to look at when we deal with the Young-Laplace equation. In short, Young-Laplace equation is used to describe the equilibrium shape of the liquid droplet, okay, or the gas bubble, due to net pressure and surface tension force, right, acting at the interface, okay. So one can list many applications when it comes to Young-Laplace, but I have listed few based on the application in medicine, where the concept of Young-Laplace, the principle of Young-Laplace equation or the principle of Young-Laplace is applied in the field of cardiovascular physiology or respiratory physiology, right? You can refer to any textbook for the application in detail. But right now, what we will do is we'll try to understand how we can actually obtain a simple relationship between pressure and the surface tension. Okay, right. So let us look at a different scenario as we have schematically shown here. Let's say we have case 1 scenario where you deal with case 1, situation like case 1 and situation like case 2 and case 3. So in these cases, if you look at the pressure that is acting on the surface, let's say for example case 1, you see that here in this case the pressure acting on both sides are equal. In such scenario, one would expect flat interface, right? Because the pressure effect is actually eliminated because both the pressure acting on both sides are equal, right? So So we can say that this is mostly applicable in flat interface case. Whereas you consider another scenario where we experience, curvature. Okay, we deal with the curvature where in this scenario, you expect that the pressure, acting at the top is greater than pressure acting, upward, right? On the other side, we have a scenario where we might deal with, let's say, geometry curvature similar to case 3, where the pressure acting downward may be lesser than pressure acting upward. Okay, but not only pressure force that are acting on these surfaces, there is another force that is also, existing, right? That is nothing but gamma, which is nothing but surface tension force, okay, which is acting at the interface. All right. Now, if you were to perform a simple force balance, on these curvatures, or various geometries, you would understand that it is simply nothing but you also have to include gamma, which is nothing but outside pressure and area corresponding to a given area, and inside pressure, okay, acting on area which is acting downward, and then you also have surface tension force multiplied by perimeter. So this if you perform a simple force balance, you would achieve an equation of this kind. Now we know that whenever we deal with a case where the surface or interface is considered, we know that work is being done by the system, because surface tension usually pulls the surface down because of the surface tension effect, right? So you consider that as in such case we say that when we consider that work is being done by the system. Apart from that, you also have to consider the pressure force that is acting from both sides. So it could be work done on the system as well as work done by the system. So in such scenario, you will have work done due to delta P and work done due to gamma. So we know simply the work done is nothing but gamma dA, okay? And this work done can also be expressed in terms of the change in pressure and change in volume, which is nothing but delta P into dV. If this is going to be our governing equation, then how we can get a relationship between pressure and gamma in a more compact form, right? This is a differential equation, but we need to obtain general equation, okay, in a more compact form, right? So what we will do is we'll start with a simple, since we are going to deal with a general equation, for a general case, we'll start with a curvature, okay, where we will deal with, we will deal with two major axes, right, predominantly, because if we talk about spherical geometry, where the radius, right, radius is, both major axes is of same radius, right? Whereas if you talk about cylinder, the major axis, there is major axis and there is minor axis, okay? So since depending on the geometry, one would have to choose a suitable, equation. So for that, what we can consider is we can take a curvature, right, which has got two, primary axes, right? So with respect to the center of axis, one would get two primary axes, right? Okay. So this we will take for an example, And if I name this, a geometry like rectangle-like geometry, okay, this is infinitesimally small, element, okay, control element. So we can also say that it is nothing but a rectangular geometry, but it has got two major axes, primary axes, right? So in the first case, if I name this as AOB, this triangle will have angle alpha, whereas the other triangle will have angle beta. Okay, right? The length and breadth, so the AB, okay, the distance from A and B is X, and B and C is Y, right? Then the area here is simply XY. Okay. Now this is a time t equal to 0, right? Now let's say that after some time we impose a small perturbance, right? Like you consider that there is a pressure force as well as surface tension force acting on this surface. So which will make the surface deviate from the existing, right? So there will be change in area, right? And there will be displacement, basically a deformation or displacement will occur. Okay, so if I consider that after some time t equal to some time t, so what will happen is, let's say, either you will get a positive curvature or negative curvature. But let's understand that the curvature that we will get is let's say bigger than this. Okay, yeah. So I'm trying to just draw a similar geometry, somewhat bigger than this. Okay, so in this case we have a triangle. Okay, this is just a triangle. I'm sorry. Yeah. In this case, we get a triangle, similar triangle, that is A dash. If I call this as A dash, B dash, C dash, and D dash, this will be O dash. Okay. So we set, in this case, what we assume is that when there is a change in area, or there is displacement with respect to the curvature because of the pressure force and surface tension force, what we try to propose is that they increase or they decrease, but they proportionately change, right? Which means that the angle in which they form is same as the existing one, right? Let's say this is also alpha, this is also beta. So this angle and this angle is same. This beta and this beta is same, but they proportionately vary such that only the distance between A dash O dash changed little bit, right? Right. If I call this as R1, A to AO, if I call AO, the distance between AO as R1 and distance between O and C as R2, then since it is proportionately increasing or decreasing, I would call that as the distance between A dash and O dash, I would call it as A R1 plus DZ, whereas the distance between O dash and C dash will be R2 plus DZ. Okay. So the assumption here is the angle doesn't change, but only they proportionately vary, right? So in this scenario, we can, have the following propositions. Like, for example, let's say I know sine alpha in this case will be x by R1, okay? In this case, sine alpha will be x plus, okay, so this one is, if this is x plus dx, and this part is y plus dy, okay? Right. So in this case, sine alpha will be x plus dx by R1 plus dz. Since sine alpha is same, that is a proposition we set in this case. In such scenario, you will have x plus dx by r1 plus dz equal to x by r1. Similarly, if you say sine beta equal to sine beta, at both instants, right? Then you can say that sine beta is nothing but y by r1, r2, and sine beta in this case y plus dy divided by r2 plus dz. So this is the proposition that we follow in this case, right? So simply what one would get is x plus dx divided by r1 plus dz equal to x by r1, y plus dy divided by r2 plus dz equal to y by r2. This is this is the relation we obtained from these propositions. Now we go back to the equation that we initially started with, that is nothing but delta p dv is equal to gamma dA. This is our governing equation. Now we know what is dA. dA is change in area. We know change in area because it changed from the curvature. It changed from this geometry to this geometry, right? So then dA will be simply nothing but x plus dx into y plus dy minus xy, right? So if I simplify this further, this will be simply xy plus x dy plus y dx plus dx dy minus xy. So I can cancel xy and xy because this is dx dy. Dx itself very small. Dx dy will be negligibly small, so we can actually ignore this one. Then what we will be left with is x dy plus y dx, which is nothing but dA. Okay. Now we know delta p is nothing. Delta p into dv can be written as xy into dz. Okay. In such case, this will be simply nothing but gamma into x dy plus y dx. Okay. Right. So delta p here is nothing but gamma into it is simply nothing but dy by y dz, okay, plus dx by x dz. Now we are left with one step, that is we need to know what is y dz and x dz, right? Then we will be able to get the general equation, Young Laplace equation. So for that, what we do, we resort to the proposition that we set, that is x plus dx divided by r1 plus dz is nothing but x by r1, all right, and y plus dy y plus dy r1 plus dz is nothing but y by r2. So this is what we have. So if I simply simplify this, I would get x plus dx into r1, which is equal to x into r1 plus dz. Okay. So similarly, if I just try to simplify this, I would get minus x r1 minus x dz, which is equal to 0. X r1 can be cancelled. X dz is equal to r1 dx. Okay. Similarly, if you do for other cases, you will get y dz is equal to r2 dy. So if I substitute back, then I would get delta p is nothing but gamma into I have dy by y dz. Okay. So dy by by y dz is r2 dy plus dx by x dz is r1 dx. Okay, so then simply I will have delta p, which is nothing but gamma into d 1 by r1. Okay, 1 by r1 plus 1 by r2 itself. So this is our compact Young Laplace equation in general case. Let's consider limiting cases. Let's say we deal with cylindrical geometry. Okay, cylindrical geometry. In such scenario, you have the major axis will be infinitely larger than the minor axis. So mathematically we can say that R1 will be tending to infinity. In such scenario, we will get delta P nothing which is equal to gamma by R1, right? This is for the case of cylinder. Now, if you deal with spherical geometry, okay, in such scenario, we know that R1 equal to R2 equal to R. So we can simply say delta P is nothing but 2 gamma by R or RS, right? Okay. In case of flat surface, a flat geometry, right? Okay, flat surface, since both axes tending to infinity, okay, you can say that delta P is simply nothing but 0. Okay, so depending on the situation, depending on the geometry that we deal with, one would get a different compact equation. Okay, this is nothing but Young Laplace equation. All right, so now what we will do, we will move on to the tutorial part today. So here we have given the problem where we are asked to find out the pressure, okay, or compare the pressure outside. Okay, so in two cases, one is we have got the spherical bubble. Okay, in first case, the diameter of the spherical bubble is 2 mm, okay, which is a macro bubble. In another case, the diameter of the bubble is 20 nanometer, okay, so nano bubble. So in these two scenario, okay, what is the Laplace pressure? That is what we have to calculate in this. So we know it's spherical geometry, curvature, okay. We can straight away take the compact equation, that is delta P is nothing but 2 gamma by Rs, okay, which is nothing but 2 into gamma in this case, since it is for water in this case, so for pure water, so the air-water interface, the interfacial tension, right, in this case will be 72 milliNewton per meter. So one would take 0.072 Newton per meter divided by the radius, right? Radius of the curvature is given, which is 2 mm. Diameter is 2 mm. So you can take radius as 1 mm, so which is nothing but 10 power minus 3. Okay. So in this case, one would get 10 power minus 3 into 10 power 3. So it is simply nothing but 144 Pascal, right? So you can say the pressure outside compared with the pressure outside, maybe you can one step further, you can say that pressure outside will be 144 plus pressure inside, right? Okay, you can also say in this way, or you can keep it simply delta P in this case is 144 Pascal. What about the other case, which is nano bubble, or the bubble which is in 20 nanometer in diameter? So in this case, the delta P is simply nothing but 2 into 0.072 divided by, since it is diameter, I can take 10 nanometer, right? So 10 into 10 power minus 9 meter. In this case, I will have 144 into 10 power minus 3, okay, divided by 10 power minus 8. So this will be simply 144 into 10 power 5 Pascal, or it will be simply 14.4 megapascal. Okay, see the difference. In the case of 2 mm dia, in the case of 2 mm dia, you can see that it is simply 144 Pascal, whereas in the case of 20 nanometer diameter bubble, you get that the pressure inside is, so too large, right, compared to the macro bubble, which is 14.4 megapascal. Okay, so this is purely due to the curvature effect. Okay, so thanks to Young-Laplace equation, using which we can we be able to calculate what is the the compact pressure, what is the pressure inside the bubble or the droplet. So we'll stop here. I think this is very clear to you. So we'll stop here. We'll see from the next lecture. Thank you.